Okay, I'm going to hand back some homework. Here's your first assignment that I have graded, and also I have some solutions because I think maybe one person got them all right, or one or two maybe. But anyway, I'm handing back. Generally I'll probably hand back solutions. I just mentioned this in the computer systems class, but this one it applies even more so. There's going to be lots of ones and zeros floating around here, guys, and there's lots of details, and it really helps if you're meticulous and very careful and get all the ones and zeros right. So make sure that you look at the solutions, and if you made a mistake, make sure you go back and correct it and see me if you need some help. There is one thing that I've kind of noticed. This happens quite frequently. You guys, if you have some gates like if you have an AND gate like this and another AND gate, I need my own template here. It's hard to get these right. Hard to get the proportion right. Anyway, and if you have some, and suppose I've noticed this. Some people would do this. They want to connect this wire to something down here, and so you go around like this, and do all this like this. Look, you guys, let me just to be kind of professional about this a little bit. In a circuit diagram, in a drawn, when you draw a circuit diagram, first of all, the lines never curve. I've never seen a logic circuit drawn with curved lines. They're always either horizontal or vertical. So if you want to get in the habit of having your stuff look really professional, I don't care. I'm not going to count off or anything. Then your wires should all either be horizontal or vertical. And furthermore, if you want a wire to go this way, you can just go ahead and have it cross over these. The convention is, and when you draw these, the convention is if one line crosses another line, we assume it does not contact. We assume it does not make contact unless you draw what?
A dot.
Yeah, unless you draw a little solid dot there. That means that they're contacted. Do you see what I mean? So if you want to sort of get in the habit of drawing good circuit diagrams, the way it's done, the way it's always done, and I tell you, I used to see, but this doesn't happen very much anymore, but you can tell when somebody has written a book and doesn't really have any industry experience or whatever. Some books used to do this. Have you ever seen this? Boop, boop, to show that it jumps over. But nobody, don't do that. I don't see that very much anymore, but anyway, that's kind of amateurish. And the other thing is, I've noticed that some people are in order for your here again, I'm not going to make points for this, but it's also if you want a little exercise in neat logic diagrams, try to minimize the number of corners because the wires all should be horizontal and vertical. See if you can lay it out so that there's as few corners as possible. And frequently what that means is offsetting a couple of gates at two different levels. Like if this goes into another gate, see, then this doesn't have to have a corner if this one is up a little bit from that one. See what I mean? So anyway, some little Eloise household hints. So this next figure that we're looking at is figure 10.21. And this has to do with De Morgan's law and the implications of De Morgan's law in a logic diagram. Now check this out, you guys. In part A of figure 10.21, the Boolean algebraic expression is quantity A and B and C prime, right? So what kind of a gate is that? That's a NAND gate. You AND them and then you negate it, right? So here's a picture of the NAND gate. Are you with me? But on the other hand, we know by De Morgan's law that if you invert A and B and C, what do you get? A prime or B prime or C prime. Now, if I ask you to draw a logic diagram of A prime or B prime or C prime, you would draw it just like this bottom figure in part A. This, well, the way you say this is an inverted input OR gate. So it's as if those inversion circles are coming in from the inputs, and the inputs are being inverted, and then it's going to an OR. Are you with me on this? So do you see that if you did a truth table for A and B and C prime, that would be the exact same truth table because they're logically equivalent, right? So a manufacturer, there is no, like a manufacturer would never manufacture a NAND gate and then have another part that he would manufacture that would be an inverted input OR. He'd never do that. Why not? Because it's the same gate. I mean, it's the same gate. It's logically, you see what I'm saying? I mean, the transistors would all be the same, right? It'd be doing the exact same thing. So, but we know now from De Morgan's law that a NAND gate it does the same processing as an inverted input OR. So you can draw, and sometimes you see the gates drawn this. Sometimes you see a NAND gate drawn like this. Are you with me? Yeah, question?
In the homework, if you want to, like, this isn't on the homework, but for example, if we had a B or A prime B prime, to do it for the two-level circuit, would you want us to do A, B, and then have two inverted inversions for the inputs for if we were doing A prime B prime, or just write A prime?
No. Those are usually abbreviated. Just write A prime B prime. Okay. Don't write A and then the inverted. Yeah.
So two-level circuits.
Two-level circuit. I mean, because these two-level circuits are 99.9% of the time they are abbreviated. They are abbreviated circuits. So yeah. So just do the A prime. Don't have the A coming in with a circle.
Got it.
Yeah.
Thank you.
Is everybody clear? See how this works? But look, for every principle. For every digital logic principle, there is a what? A dual principle, right? So what's the dual of this? Well, so figure 10.21b, what do we have? A or B or C, that whole quantity prime. Are you with me? But we know by De Morgan's that's A prime and B prime and C prime. Well, what is A or B or C prime? What kind of a gate is that? A NOR. Yeah, that's a NOR here. But that's equivalent to a what? An inverted input AND. So sometimes the NOR gate is written like this. Are you with me? Now, get this, sports fans. Let's carry this to the next level. And by level, we mean level, how many gate delays? 2 levels from the input to the output. 2 levels of gate delay. 2 gate delays from the input to the output. And look at this. In figure 10.22a, here we have an AND OR circuit. Are you with me? So we have A and B and C coming into one AND gate. We have D and E and F coming into another AND gate. And we have each one of these going to an OR gate. So the Boolean expression for that circuit is A and B and C or D and E and F. Right? But look, if we do De Morgan on this plus double negation, that's the same thing as what? A and B and C prime and D and E and F prime, the whole thing prime. All right, but look. So what is A and B and C prime? What kind of a gate is that? That's a NAND. And then D and E and F prime, that's another what? NAND, and then we AND that and negate that, and that's another what? NAND.
Got it.
Do you see how that works? So look, instead of constructing an AND OR circuit with 2 ANDs and an OR, we can just do NANDs. we replace these ands with an and, we replace that or with a NAND, and this does the exact same thing. Now, isn't that slick?
It's pretty cool because in on a chip, unlike 7400, you could just do a two-level circuit on one.
With one chip. And that remember in the lab we had the quad 2-input 7400?
Yeah.
Yeah. So, yeah, exactly. So, exactly, you could do it with one chip. Good point, like in the lab. All right? So that's just a mechanical, because of this mathematical relationship or logic relationship, it's just a mechanical thing. If you have a two-level and or, you just draw them with all NANDs. Now look at here, and look at part C of the figure. Check this out. What did we say was a different way to draw a NAND? A NAND is the same thing as a what? Inverted input OR. Inverted input OR. So if we take this second NAND and draw that as an inverted input inverted input OR, then what does it look like? These NAND gates have the same shape, geometric shape, as these AND gates in part A. Are you with me? And this inverted input OR gate has the same shape as the what? The OR gate in part A. And furthermore, you can see that this little invert circle on the AND does what? Cancels out the little invert input on this, and this looks like, so this has the same shape as an AND OR circuit because we drew this second level NAND gate as an inverted input OR. And so it's shaped, if you look at the shapes of the diagrams, and sometimes the shapes look like an AND OR. And sometimes, you will see this actually in digital circuit design. You see in digital circuit design, you will see this occasionally. It's not that it's not super common, but it is common. You can see if somebody wants to, if the designer wants to emphasize the function of the circuit, they'll sometimes draw an AND OR circuit with NAND gates, but they'll draw it as in part C of this figure. Is everybody clear on that? Now, and not only that, watch this. Not only can you have any two-level circuit represented with a NAND gate, with a two-level NAND, but what about one gate? What if you were trapped on a desert island? What if you were stranded on a desert island, as in, what was that movie where? Castaway. Castaway. What if you were stuck on a desert island, and the only thing you had was a box of NAND gates? Would you be up the creek without a paddle because you couldn't do a NOR, and you couldn't do an OR, and you couldn't do an Do we have wires? And you had wires, yes, and you have wires. Yeah. Well, look, check this out in figure 10.23. If you need an inverter, what can you do? If you need to do a function that does A prime, what could you do? Well, you could just take these two inputs of the NAND and do what with them? Connect them together and have that come in from the left. Are you with me? Now, so what are you doing? You're taking A, and then you're inverting it, right? But what do we know about A and A?
It's just A.
It's just A. By what property?
0.
No. No. Idempotency. By the idempotent property, A and A is just A. So that's A prime. So, and here's another thing. Suppose you're in the lab, and you have a NAND, NAND gate, and you need an inverter. Well, you could plug in. What was that? Was it a hex inverter? Was that the chip that had 6 of them on one chip?
I think so.
It was a hex. And you suppose you didn't want to have to plug in a hex inverter. You could just do what? Take one of your leftover NANDs and do what? Hook the inputs together. There's your inverter. Are you with me on that? Do you see how you can do that? And furthermore, okay, so look, yeah, that's how you can do that. And so furthermore, and because of this NAND and OR thing, you can do anything with a NAND. The NAND is all you need.
What does it talk about doing tying unused NAND inputs to VCC and unused NOR inputs to ground? So like, is there any way of making a NAND an inverter by using the VCC, the energy
Oh, is that you're reading that from the lab?
from your lab?
Okay, I don't remember exactly what that is referring to, but I think it might be referring to this. There's another way to make a NAND. There's another way to make
NAND.
there's another way to make an inverter out of a NAND. Here, let's do it. You ready for this? Suppose you have a NAND like this. All right. Now, and you want this to be A prime. You want this to be A prime. What you can do is you can feed in A here, and this one you can tie this one to what?
Electricity?
Well, no, to what signal?
5 volts?
Yes, 5 volts. So you can make a 1 here. Because, yeah, which you in the lab you connect this to VCC. That might be what that's referring to. So if you connect this to VCC, that's a 1.
Of course.
And then 1 and A is what? What is 1 and A?
It's item or identity of.
What? Yeah, but what is 1 and A? It's A, and then inverted is A prime.
Cool.
So this is another way. This is another way to make an inverter out of a NAND.
So
You could either tie them together and have A go into it, or you could tie that to.
So by duality, you could do that with a NOR gate by attaching it to 0 or ground.
Yes.
Cool.
Yes. And yeah, and so here's the same way. Yeah, here's the same way. If you're stuck on a desert island with just NOR gates, you can make an inverter the same way. Okay, and so these do the same function as this. Okay, and now that 2-level stuff, there's by duality. What do we know? It's the same principle, right? Only this time, instead of applying it to an and/or circuit, we're applying it to a what? Or and circuit. Are you with me? So check this out. In figure 10.24, what we have in figure A is an or and circuit. So what do we have? A, B, C coming into one OR gate, D, E, F coming into another OR gate, and then these two feed into an AND gate, right? So what is that algebraically? It's A or B or C quantity and D or E or F. But we know from De Morgan's law that that's the same thing as A or B or C prime or D or E or F prime, the whole thing prime, right? Because if we do De Morgan on that, it's and double negation. It's, the same as that. So, but what is A or B or C prime? That's what kind of a gate? That's a NOR gate. And then if we OR them and then prime that, that's another NOR gate. So we can just replace, so anytime we have an OR AND circuit, we have an equivalent NOR circuit, right? So we can just replace these with NOR gates, right? And then in the same way that we can draw it to look like, we can draw the shapes of the gates to look like what we had in part A, we can take the second level NOR gate and do what? Draw it as a inverted input, and now that has the same shape as that. So I think you had an exercise that said draw something with only NAND gates or something like that. So now you see how to do it. You just, if you have and or, you just change them all to NANDs. That's how you do it.
Mm-hmm. Okay if in the NAND you use the NOR gate? Because that's the same thing, or do you want it all with NAND gates?
All with NAND.
Okay.
You mean wait, you mean inverted input or?
Yes.
Yeah, because I mean, it's simple.
Do you mean a NOR gate or an inverted?
Well, wait. Let's go back. I think your homework. Did you have a homework assignment that was that used this principle of figure 1022?
Yes. Yes.
Yeah. So if you draw C, is that okay, or do you want it to be all the the same as B?
Either way is fine, because they are equivalent, because this gate is that gate.
Yes.
This is a NAND gate. It's another way to draw a NAND gate.
That's not an OR. That's an
Yeah, this is not a NOR, this is an inverted input NOR.
OR.
I think,
Inverted
or,
input.
sorry. Gee, you're right. Yeah, this is not an OR gate. In part C, the second level gate is not an OR gate, it's an inverted input OR gate, which is a NAND gate. So that's just another way to draw a NAND. Actually, I prefer, you see what I'm saying? Actually, I prefer you to draw it just with all NANDs like that, but either way is fine. Okay? Now, there's one more thing that I think I want to mention, a little tip that about your homework. If you ever have an expression like this, let's say you have A or B and A prime or B, something like this. If you ever have an expression like this and you want to get rid of the parentheses, here's what's cool about the way they represent the operators and the precedents in digital logic design. Do you know how in algebra, when you had addition and multiplication, how would you get rid of the parentheses here? What was the rule that you used?
Distribute.
Yeah, FOIL. And FOIL was what? First, outer, inner, last. Basically, that's the distributive law twice. And so now that we're kind of like, using plus kind of like or and or, and times kind of like, anyway, you can do it. You can do FOIL. And so this would be, but it's with and. So it's A and A prime, or what? A and B. Now make sure to do it in alphabetic order. This would be what?
A prime.
Or A prime and B, or B and B. See, so that's a handy little shortcut.
So we're just allowed to write FOIL?
Yeah, or distributive.
Twice.
Yeah, distributive twice. Either way. And furthermore, once you get good at it, actually, let's think about how this would be. What is A and A prime? You should know this right now.
Complement by conjugation.
Is 0. A and A prime is 0. And what's 0 or anything? Just the other thing. So when you do this, you just drop it.
Are you okay if we skip steps like that?
Sure. I'm okay if you skip steps like that. Just so long as it's correct. Just is everybody clear on how that can help? You see how that can help you with your manipulations? Okay. So now, are there any questions about the homework that's due today? Any more questions about the homework due today?
No, we're good.
Okay, so are we good? All right. Excellente. So now we're going to start on our next step in our journey. Now, hopefully, what we've learned so far is there a one-to-one correspondence between a truth table and a Boolean algebraic expression, yes or no?
No.
Correct, there is not. Is there a one-to-one correspondence between a truth table and a logic diagram, yes or no? No. Is there a one-to-one correspondence between, there's only one. Is there a one-to-one correspondence between, what is there a one-to-one correspondence between?
Logic diagram.
Yeah. Boolean algebraic expression and logic diagram. Okay, so now, what this means, okay, and what we have discovered through all these manipulations is that any Boolean expression or any logic diagram can all be written as an equivalent, how many level?
2 level.
2 level, right? We've seen that anyone can be written as a 2 level and or, and we've seen algebraically how to write it also as a 2 level what? Or and. Now what is the significance, and here in figure 10.24 is an example, this is an or and. And what is the significance of that? What is the significance of being able to reduce every combinational circuit into 2 levels in terms of what's practical in a logic diagram, in a logic design? problem. What's the significance of that?
Efficiency.
Yeah, and what about efficiency? How does that work?
Gate delay.
Gate delay. So what is the gate delay?
The more gates there is, the more delay.
Yes, the gate delay, and what is the definition of a gate delay?
What comes in the same time as goes in?
Yeah, what comes out doesn't happen at the same time as a change on the input. So what is the gate delay? Between what about the input? A what and the input?
Change.
A change. So it's the amount of time it takes a change in the input to do what?
Propagate.
Propagate to the output.
Output.
Output of a gate. Is everybody clear on that? It's the time it takes a change in the input to propagate to the output of the gate. All right? Now, and so, oh, and by the way, does anybody have any idea about what those times, what that gate delay, how many seconds are we talking?
10 nanoseconds.
We're talking about nanoseconds. And what is a nanosecond? 10 to the negative 9. Are you with me? That's and we're only talking single digits and maybe even fractions of a digit. So we might even be talking, what's the next one after nano? Smaller.
Just if you wanted to.
Oh, we don't know this yet? Oh, shoot, you better know that.
What class do we do that in?
Huh?
I think we did it in systems.
Oh, we didn't do that here?
No.
Oh, well, we did it in systems. Yeah, you need to know that. Yeah.
Is it pico?
Say it again?
Pico?
Pico.
Oh, pico.
Nano pico, yes. And the pico is 10 to the minus what?
12.
12. All right. So, yeah, we're talking single-digit nanosecond delays, these days. Now, okay, now let me say one simplification. Do you remember we said that electronically, the number of transistors it takes to make a NAND is actually fewer than to make a what? An AND. So inside the chip, the way how do they make AND gates? They actually have to make a NAND gate, and then inside the chip they put an extra inverter on it, and that turns it into the AND gate. So that's another reason to have things always done with NAND gates. Do you see what I mean? Because actually the gate delay of a NAND is a little bit less than the gate delay of an AND. But now here, you guys, here's what we're going to do. We're going to simplify, all right? So from now on, here's what we're going to do. And this is a simplification, but because we just need to learn the principles and not be too concerned about we can always refine it to be more accurate if we wanted to. But we're going to simplify. We're going to assume that every AND gate and OR gate and XOR gate has one gate delay, and that they're all equal. AND, OR, NAND, NOR, XOR, all those gates have one gate delay. And we're going to ignore any gate delays through an inverter. Except there might be an exception to that rule a little bit later on. But generally speaking, that's what we're going to do. Are you with me? And so what we are going to want to do is we're going to want to count gate delays between the input, the change of input, and the number. And so what we want to do is we're going to have to find like the longest path. You see, the longest sequence of gates that the signal has to travel to get to the end. And that will be how fast it takes that combinational circuit to do its processing, and we'll do it in terms of gate delays. And depending on the technology, that gate delay could be small or large, but for a given technology, that's what we want to minimize the gate delay. Are you with me on this? Mm-hmm. So, with that simplification in mind, what we want to do is the following. Here's our task. With that in mind, what we want to do is this. We know that any circuit, no matter how complicated, can be reduced to just 2 gate delays. Either a what? An and, or a what? Or and. Now, it turns out that it's possible to have 2 and or circuits that do exactly the same thing, but one uses fewer gates than the other. Now, let that sink in a minute. It's possible to have 2 circuits that and both of them are and or, and because both of them are and or, that means how many gate delays? 2 gate delays for the processing speed, right? But one of them uses more gates than the other. Now, how can that be? That means one of them would have what?
A lot of different.
A lot of and gates, a lot of different and gates, or it might have some and gates and some of them have what? More.
Ors?
No, there's always just one
Yeah,
or.
so it's-
Always just one or.
More inverters.
Well, no. More inputs. You get 2 input and, 3 input and. You see what I'm saying? More inputs. So, is everybody with me? But for our purposes, we're going to assume that each one of those has, what is the processing speed of each one of those 2 different circuits? They're the same, 2 gate delays. So obviously, if one of them uses more gates than the other one, and they each have 2 gate delays for their processing efficiency, which one would you want to do? The one with the less gates. Are you with me? So what we want to do, here's what we're up against. Here's what we're going to do. There is a very well-known procedure for discovering that minimum, that circuit, that 2-level circuit that has uses a minimum number of gates. And furthermore, we are not trading off. This is not a space-time trade-off. I want to make. Does everybody understand what we're talking about? Space-time trade-off? What's the general principle of the space-time trade-off? If you can have more what? If you use more what?
Space.
More space, you can have it,
Faster.
you can make it faster. This is not the space-time trade-off. Why not? Because both of them are what? Both of these circuits are what? 2 gate delays.
So time-wise, it's the same. It's just.
So time-wise, it's the same. We are minimizing the space, and we're not sacrificing any time. So there is no good reason to not minimize this way using this. Now, is everybody with me on this? Does everybody see the idea there? Okay, so this is like, there's no trade-off here. Sometimes when you minimize one, you're trading off something else. Okay, I'll take bigger space, but I'll have faster time. But no, here it's possible to have 2 circuits. Both of them have the same time. Might as well use the one with the minimum number of gates. Is everybody with me on that? Okay, good. All right, so now that's our journey. Now we're going to need a few tools. And the first thing that we have to learn is what is a canonical expression? Okay, and so this is just some jargon. These are just definitions, okay? First definition is called a minterm. Okay? Now, a minterm is a term in an and or expression in which all input variables occur exactly once. So let's do an example. Let's do an example of each one of these. Suppose we have 3 inputs. 3 inputs, A, B, C. All right? Now I have a question for you. A prime B, is this a minterm, yes or no?
Yes.
The answer is not a minterm. Why not?
Oh, because you said all input.
All inputs happen exactly once, right? Now, okay, is everybody with me?
I didn't see
input ABC, okay? Now how about this one? A prime, B, C, or A, B, C prime. Is this a min term?
No.
Not a min term. All right? On the other hand, how about A prime, B, C? Is this a min term?
Yeah.
This is a min term. A min term. Now, does everybody see what a min term is? And how about this? A prime or BC. Is this a min term? No. It's not a min term. Because it has to be an and. It's a term in an and or in which it's, you know how, yeah, no, this is not a min term. This is the min term.
Oh, it's a single
this,
term.
it's a single term.
Okay. That makes
Actually, this is not even an or of two min terms. Okay?
Well, why not?
Well, this one's not a min term.
Oh, I see what you're saying.
This is not a min term.
Right, it is not an or.
This, because it has an or in it.
Because it doesn't have all of them. I got it.
Is everybody, yeah, you still have a question?
The second one is an or of two min terms.
Well, it is an or of two min terms, but the whole thing is not a min term. Oh, yeah, good distinction. Is everybody clear on that? So, yeah, this whole thing is not a min term, but this is an or of two min terms. Okay? This one is a min term. This is not a min term. You know, and how about this? How about A prime, B, C, the whole thing prime? Is that a min term?
Yeah.
No, it's not a min term because it's prime on the whole thing. This is not. It's not an and. This is not a min, because if you were to expand this out, you would. You see what I'm saying?
It would be or.
Yeah. So this is not. So this is not a min term. This is not a min term. Okay. Now, is everybody clear on what is a min term? Okay. So a min term is a term in an and or expression in which all input variables occur exactly once. Now, so there's our example of a min term. Okay. Now, a canonical expression is a what? An or of min terms in which no two identical min terms appear. All right? So let's see what we have with canonical expressions. A prime, B, C, or A, B prime, C prime. Is this a canonical expression?
Yes.
Yes, canonical. Is everybody with me?
Mm-hmm.
Is this A prime, B, C, or A, B prime? Is this canonical?
No.
No, because this is not a min term. Is everybody with me on that? So this is not canonical. Okay, and how about this? A prime, B, C, or A, B prime, C prime, the whole thing prime. You know this one now, right? Not canonical. Is everybody clear on that? Okay, how about this? A prime, how about this? A prime, B, C prime, or A, B, C prime, or A prime, B, C prime. Is this canonical? Not canonical. Why not?
The first and last.
Because that appears, right? Not canonical. On the other hand, look. This is not canonical. But on the other hand, what is this equivalent to?
A canonical term.
Yeah, actually, because what is this or this? By idempotency, this is what?
A prime, B, C prime.
A prime, B, C prime, or A, B, C prime. So this is canonical. Now, is everybody clear
So
on?
essentially, the final answers we get when we're making an and or, that final statement, Boolean expression, is canonical?
Well, no, this is not canonical. You might have gotten something with just two.
That's true, I suppose.
Now, you could always turn this into a canonical expression. How would you, actually, that's a good question. How would you turn, Boolean algebraically, how would you turn this into a canonical expression? You'd take this A and B prime and then do what? And what? No, and 1. And then how would you write that 1? C or C prime in parentheses, and then distribute it, and this would be A and B and C, or
A, B prime,
A and B prime and C prime. So you could turn it into a canonical expression. We normally don't do that, but you could.
A single midterm is not canonical.
Actually, that's a good one. Au contraire. A prime, B, C prime. Is that canonical?
Sure.
Yeah.
But it's not, there's no or.
Well, I know, but yeah, there's 0 ors. 0 is a number. Are you with me?
Yeah.
See, so anyway, this is canonical. Yeah, good.
And a midterm?
And a midterm, yeah. A single midterm by itself is canonical. Now, is everybody clear? Now, here's the thing. A canonical expression is directly related to a truth table because each midterm in the expression represents a 1 in the truth table. Right? Now, here's another thing, you guys. There is a really slick shorthand abbreviation for canonical expressions. It's called the sigma notation. Now check this out. Let's look at figure 10.25. I think figure 10.25 is the table. Now, do you see that here we have a 3-input function, A, B, and C. Oh, and by the way, that's the other thing I wanted to mention. Anytime you draw a truth table, always draw it, well, there's going to be a few exceptions in the future, but unless otherwise, usually well, how do I say this now because I can't say always. Okay, for now, always do it in this order. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now, why do we want to do it in this way? Because in decimal, it's 0, 1, 2, 3, 4, 5, 6, 7. Are you with me? So look, this whole truth table has zeros in some places and ones in other places. So now, what symbol do we use for or in our logic Boolean algebra? What symbol do we use for or? Plus. And what does sigma in math represent? Summation. So now sigma represents not summation for us now. What does our sigma represent? Or. So look at this sigma notation. Well, the way we write this is x of a comma b equals, we put sigma, capital sigma, parentheses, and just 3, 6, 7. Look, this one little tiny expression, sigma 3, represents this whole truth table. Now, isn't that compact?
That's cool.
So there's going to be a whole lot of problems now in the future where you're going to, instead of giving you the truth table, we're just going to say sigma 367. Boom. Is that cool? It's just a really compact notation. Very useful. Instead of having to produce the whole thing. And furthermore, if there were 4 variables, x, a, b, c, d, it would be the same thing. Only instead of going from 0 to 7, it would go from what? 0 to 15. All right. And if there were 5, it would go from 0 to
And we won't use
31.
a similar notation for or ands.
Yes, we will. And what will that notation be? We will use it. The question is, we won't use that a similar notation. Well, we won't use sigma for or and,
Right.
but what will we use? Pi, because pi is the product, right? The uppercase pi. Yeah. So in fact, check it out. If sigma is 367, 367 is where this, I paid her to say that. Because look, 367 is where there's a what? Is where there's a 1. So by duality, what's the pi notation?
Where this is 0?
Yeah, so x of ABC, this same function, x ABC equals pi of what?
0,
1,
1,
2.
2, 4, 5.
Boom. Are we good? Does everybody see that? All right, so there's some, and I think you have an exercise to draw something. And so does everybody see that pi 0, 1, 2, 4, 5 equals sigma 3, 6, 7? It's the same function. Yeah, it's just a shorthand. Okay, now here's how, so that's one, there's some notational tools for us and some definitions. And everybody understands that these are, oh, by the way, let's go back and take a look at min terms. What is, if we were to write this out algebraically, how would we write this out in canonical notation? What would this function x of ABC equal?
A prime B C.
A prime and B and C, or
A B.
A and B and C prime, or
A and B.
A and B and C. And do you see that those are min terms? Are you with me? So it's very easy to write that as min. Okay? And now what would this be? This would be what? What would it be? It would be A, now it's the zeros, so would it be A prime or?
B prime or C prime?
Or would it be A or B or C?
I thought it was A or B or C.
We have to think this through. How do we know if it's A or B or C? What would this, would it be? It would be A or B or C, because this is only 0 when this is 0 and this is 0 and this is 0. Yeah, so it's A or B or C and what?
A or B or C.
Yeah, A or B or C prime, and etc. Yeah. Actually, this is a good place to stop. So what we're going to do tomorrow is we're going to learn another tool called a Carnot map. And a Carnot map is going to help us do that minimization process that we described a few minutes ago. All right? Good deal. See you tomorrow.